You probably can. Hey, Daniel. We have 5 homework problems left. 38, and then these guys. This is on 3-3, page 144. We have 5 homework problems left, and I was going to wait and do all of them and then record. But I don't know if you're going to be able to decipher all my work if I wait till then. So, whatever. 38 looked like this, and we did the product rule. And then I went through and I distributed this guy through because I'm just like, well, let's try it. Let's see what this looks like. And I distributed this guy here and this guy here and this guy here. And it just so happens that like these pieces cancel and these pieces cancel. So this is your final answer. So that's kind of exciting. So look through, and if you need to pause that video, you can to see what all our work is. But look through and do that problem and see if you come up with the same answer as what we did. Okay, now this one, I'm going to get rid of some of this stuff here. Oh, come on. Okay, so this was the rule for the derivative of inverse cosine, right? So we did inverse cosine, and then the u part is going to be just the stuff that's underneath, okay? So we did negative, right? Negative, right here, 1 over the square root of 1 minus u squared, which is cosine squared. So that's what we have right here in the blue, right? Times the derivative of the u part, which is negative sine, okay? So we've got like this blue piece going on right here. Right? But then we said, okay, wait a second. 1 minus cosine squared, this is a trig function right here. 1 minus cosine squared is sine squared. So we're like, okay, this thing right here is sine squared, but then we're taking the square root, right? The square root of sine squared is just sine, 1 over sine, right? So we've got that times negative sine, and negative 1 over sine times negative sine is just 1. So like our derivative and derivative of everything is just 1. But we could have done that to start with because inverse cosine and cosine cancel each other out. So we just have x, right? Y equals x. And the derivative of x is 1. So that's kind of fancy. This one here, we have the inverse secant of x. And this is the like rule for inverse secant, right? 1 over the absolute value of u, and u is that x to the 5th power. So we've got this right here, right? 1 over absolute value of u times the square root of u squared. So that's x to the 5th squared, which makes x to the 10th, minus 1 times the du dx, which is the derivative of x to the 5th, or 5x to the 4th, and we just lumped him on top. And so we made him look like that. So kind of gross, but that's what he turns out to be. Okay? All right, last two. Ready? 50. This one, right here. Okay, here's 50. Go. Shh.
Good that.
Shh. Shh.
You started that and you know it.
All right, go.
Yeah.
What's the, what do we do?
You get it.
This one, 50.
Oh, yeah.
How do you want to tackle 50? Should we do a quotient rule, maybe?
No,
Like, we could move him to the top, but then we got another negative 1 power, and I don't want to do that.
Gotta be safe now.
I suppose.
No drums for you.
Oh, no, I know. What's 1 over tangent? What's 1 over tangent?
What's tangent to the negative?
What is 1 over tangent? What is 1 over tangent x equivalent to?
Sine x,
No,
cosine x,
no. You're getting warmer.
sine plus cosine x.
What's 1 over tangent?
Negative sign.
No. What's 1 over tangent?
Cosine x.
No.
Inverse tangent.
No.
Cotangent.
Cotangent, right?
Oh, yeah.
So,
Oh yeah, that makes sense.
so what's 1 over inverse tangent?
Negative.
Inverse cotangent, right?
Yeah.
Yeah, right? Like that means this, right? Okay, and what's the derivative of inverse cotangent? We can just literally write the rule down because it's just x, right? Cotangent, negative 1 over 1 plus u squared du dx, right? Negative 1 over, is it 1 plus u squared?
Yeah.
Du dx. Okay, what's u? Just x, right? Okay, so this is literally negative 1 over 1 plus x squared, right, times, what's du dx going to be? The derivative of this, which is just 1, or we can just leave it off, right? That's his derivative. Hey, that's kind of nice. Wow, that was a big leap to begin with. Hoofda. All right, last one, 58.
Back to 48.
Where did 58 go? I put him somewhere. Oh, hey, down here. Right here. There you go. Okay. Okay, square root of cotangent. What's our approach on this one?
the next person.
Here's a chain to the 1/2 power, right?
Sit down.
Okay.
What are you doing?
Clean up the donuts off my
Okay.
table.
To the 1/2 power. All right, we gotta do the chain rule, which means I deal with the outside first, right? So, oh gosh, this is gonna be awful. All right, here we go. What do we do first?
Half out front.
Half out front. Okay, leave the inside. Inverse cotangent of x. To the
Negative half
-1/2 power.
times.
Shh. Times the derivative of the inside. What's the derivative of the inside? Oh, that's, yeah, derivative of the inside. Isn't that what that is, right?
Except, would it be
Times -1/1 plus x squared, right? Okay. Okay. All right, now we gotta fix everything. Okay, got it? All right, I have 3 things that I'm multiplying together. I'm multiplying this guy, and I'm multiplying this guy, and I'm multiplying this guy. Got it? Okay, that middle guy, I'm gonna fix him, and I'm gonna go 1 over the square root. True?
Yeah.
Okay, I'm gonna make it like that. So if I put all of them together, what's the top?
1.
1, right? I get -1. I don't know where you want to put the negative. I put it out front. Okay. Then what shall we do?
2.
You want 2?
Can you put 2 out front?
I don't care. You could distribute the 2 through this guy if you want to.
Oh, yeah.
2 plus 2x squared times the square root of inverse cotangent. Anything else? We can't distribute him through there because that's got a square root. That it? I think that's it. Okay. So, yeah, started with the chain and then the derivative of inverse cotangent. Yeah. Okay. Can we handle it? Is it okay? I'm going to, at some point, take these rules and put them on like a half sheet of paper. And the same thing with the e to the x's and such, all of those guys. I'll put those on a half sheet of paper and you can use. Do you guys still have your other half sheet of paper too? Boys, do you still have your other half sheet of paper?
No promises.
No promises?
No
Okay.
promises.
All right. Okay.
See.
We'll see. All right. Okay. Good?
Yeah, I do.
All right. I'm going to talk related rates real quick because I want to start them a little bit. I'm just real excited about them.
You sound scared.
I'm not going to give you any homework assignment, but I'm going to talk related rates, okay?
Okay.
Because these are fun and I'm so excited. Related rates is like
You mean it,
my
or you're
jam.
just saying that?
No, related rates is like my jam. I'm ready. I'm excited. Here we go. Okay, related rates. I think I alluded to this like on like one of the first days of school. Okay, and we were talking about blowing up a balloon, right? Okay, so I'm just gonna do my example and stuff over here. Okay, blowing up a balloon. Here we go. Do I have a balloon example?
Paper roll.
Nope, I sure don't. All right, related rates. Here we go. Blowing up a balloon. Okay? A balloon. If I'm filling a balloon with air, that's going to involve the volume of a balloon, true? You know what the volume of a sphere, a balloon's not completely spherical, but whatever. Volume of a sphere is?
4/3 power.
Nice. How do you remember that?
Not slow.
Okay, cool. I'm very impressed. 4/3 pi radius cubed, right? Okay, that's the volume of a sphere. Got it?
I know Billy does.
Okay.
I'm a savant.
What?
You what?
What?
All right. Okay. Here's what's happening. All right. When you blow up a balloon, right? Like it's, and this is gonna be hard for me to draw or like talk about because Daniel can't see what I'm doing. But you know how like when you blow up a balloon, like I might be blowing air into the balloon at a steady pace, right? But it like expands really fast to begin with, and then it slowly goes out from there, right? Like it seems like, and I'm just blowing in at a steady pace, but it seems like it expands really big to begin with, and then it slowly gets bigger and bigger and bigger from there, all right? And so what is happening is the rate at which the volume changes. Rate of change of volume is constant, right? Whatever number I'm going to put in there. The rate of change of volume is blowing out at a constant rate. Is the radius changing at the same rate?
Heck no.
No, the radius like changes a lot to begin with, and then it changes smaller and smaller and smaller from then on out, right? So the rate of change of the radius is going to be different. It's going to be changing, right? Okay. The rate of change of the volume, I'm blowing it at a constant rate. So this is not changing, right? That's going to stay the same number. But the rate of change of the radius is going to be different every time, right? Like depending on how big the balloon is. The bigger the balloon gets, the rate of change goes down, right? Because the radius is not changing, okay? All right. Now, here we go. Let's talk about variables that are associated with this thing, okay? We've talked about rate of change before, right? Okay? And we've said instantaneous rate of change is another name for a derivative, right? Rate of change is an instantaneous rate of change is another name for a derivative. Got it? Okay. Now, when we're talking about rates of change, we're talking about relating everything to time. Okay? So, let's talk about if I were to take the derivative of this equation right here, like the derivative of v, the derivative of r, all of those things, right? Do you know how like when we would take the derivative of y and we would have the derivative of y be dy dx, right? That's because x was our designated variable. True? Are you watching? The derivative of y was dy dx, okay? Now, we are in related rates, we're relating everything to time. So our designated variable is time. Got it? So if I'm taking the derivative of v with respect to time, what would that look like? The derivative of the volume with respect to time, what would that look like? dv dt. Okay, even though I don't even have a t variable in this equation, it's still that volume is being related to time. Same thing with the radius. The radius is being related to time, okay? So, all right, let's talk about this thing. How do I take the derivative of that? Like, let's suppose this is an x right here, right? Like, how would I take the derivative of that? The power rule. Like, we don't need a product rule. I mean, you could, but this is just a constant, right? 4/3 pi, that's just a number. Okay? So you wouldn't have to do the product rule if you didn't want to. I could just pull the 3 down in front, right? This 3 can come down in front. What's 4/3 times 3? 12/3 or just 4, right? The 3's will cancel. So 4 pi r squared. But what's the derivative of r with respect to time? What's the derivative of r with respect to time? The derivative of the volume with respect to time was dv dt. What's the derivative of the radius with respect to time? dr dt, right? So kind of like when I take the derivative of y with respect to x, I have to put dy dx on the end of everything. Here I'm going to have to put d whatever dt, right? Got it? Okay? Now, the rate of change of the volume, that's just dv dt. The rate of change of the radius is just dr dt. The rate at which the radius is changing with respect to time, right? That's what those are meaning. Got it? Okay, let's do an actual problem so that you can see how this works. Okay, ready? Ready, Freddy? All right, okay, here we go. Let's do this example. Okay, we are draining water out of a cone. You guys have seen this before, like in an hourglass, right? An hourglass, the top of an hourglass is like a kind of a conical thing, right? Like whatever. And what happens to that sand as it drains out? If you're thinking about it, it goes zoom, right? Like as the sand gets lower and lower and lower, it like goes out really fast, right? But it's pouring out the same amount. It just looks like it gets faster, right? Okay. So when we're talking about the height seems like it's changing really slow when the height is up here, but as the height gets down here, it feels like it's changing really fast, right? Like as it gets lower and lower, the height is changing really, really quick. Got it? Does that make sense? Okay, so let's look at this equation. If this is the volume of a cone, let's talk about what we would do to take the derivative of this thing, okay? So, and everything now is with respect to time because rate of change, your bottom number is always in time, okay? So, the derivative of volume with respect to time, we denote as dv dt. True? Okay, how do I take the derivative of this? Slowly.
Power.
That's going to have to be the power rule, right? Because I have two different variables. So what do you want your f to be?
Pi thirds r squared.
This is your f, right? And this is your g. Okay, let's do it. So I have f prime g plus g prime f. Okay. Blah, 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 blah. Okay. All right, I'm going to take the derivative of pi over 3r squared. Okay, that's f prime, right? So 2 comes down in front. What's 2 times pi over 3? 2 pi over 3. R to the first power times, what's the derivative of r, though? With respect to time. Everything now is respect to time. dr dt. Every variable is going to have whatever whatever dt, right? Okay, times g, and g is just h. Got it? Okay, now we have to take the derivative of h. What's the derivative of h? 1?
dH dt.
dh dt. That's
Why
the
is this so stupid?
yeah. Okay, f is pi over 3 r squared. Okay, so let's fix this a little bit, and then we'll outline what these things mean, right? So dv dt is just by itself, right? dv dt equals, let's fix this thing. I don't know what you want to do. You want to move some variables around?
Take an h out for
2 pi over 3 rh dr dt. I'm just going to put the r and the h together, right? But that's one chunk, right? Plus pi over 3 r squared dh dt.
or not.
Sure. Okay, so. All right, dv dt is the rate that the volume changes with respect to time. Right? Which I'm going to guess if we're draining water out, the volume is changing at a constant rate. It's flowing out at the same rate no matter what, right? Okay, it feels like it's flowing out faster, right? But it's going to stay the same, okay? R is just the radius. H is just the height, but what is R? Or dr dt? Like, what does that mean? What does dr dt mean?
Oh, the radius
The rate that the radius changes
in respect to time.
with respect to time. Okay, now is the radius, so think of the radius of this water, right? Like the radius of the water is getting smaller. Radius is here. Is that radius changing at a constant amount? Like if it's going from 4 inches wide here to 3 inches wide here to 2 inches wide here and down and down and down until there's no water left. Is that radius changing at the same rate?
No.
I don't think so. I think as it gets lower and lower, it's like getting sucked in really fast. So I think the radius is changing faster the more the water flows out, right? Okay, what about dH dt? What does that mean?
Height.
That's the rate that the height of this water changes with respect to time. Okay, is the height changing at the same rate? I feel like it's getting faster. The height is increasing in rate, like as it goes down, right? Like the height is changing and becoming faster. The rate that the height changes. Now the height is going down and the radius is going down. So you know what's going to happen? That's going to be negative, right? So maybe the radius is increasing at a negative 1 inch per minute, right? To begin with, and then it's increasing at a rate of negative 2 inches per minute as it goes down and down and down, right? Same thing with the height. It's going to be negative. Okay, I'm just making those numbers up. Eventually, we'll be plugging numbers into this. Got it? What? What?
What is the jerseys for?
Kennesaw Youth Basketball. Yeah.
Just taking business from
Yeah, I guess.
opponents.
I don't know. I guess. It's youth basketball.
I got beef with them still.
Okay, sure.
I like layering.
Whatever. I don't know, they're paying a pretty penny for
Larry got
Ellie
beef
to do
with
them, so
everybody.
anyway.
Yeah, beef with
Okay,
Pepper.
here's what we're gonna do. I'm gonna skip example 1 real quick because I want you to see what this looks like in story problem fashion where it actually has numbers that mean something. So we're gonna do example 2 and then we're gonna bump back up to example 1. Example 1 will be easier, but example 2 is more meaningful because it actually has like a story behind it, okay? So we're gonna go to example 2 and then we're gonna do example 1, then we're gonna stop for the day, okay? All right, assume that oil spilled from a ruptured tanker spreads in a circular pattern whose radius is increasing at a constant rate of 2 feet per second. How fast is the area of the spill increasing when the radius of the spill is 60? Blah. So, what are we talking about? Like, what is our overall equation that we're going to be doing?
Well, area of a circle.
Area of a circle. That's what we're talking about.
Pi r squared.
Area of circle. Okay, so the equation that we're dealing with is pi r squared. Got it. Area equals pi r squared. That's the main thing that we're talking about.
How fast is the area of
Okay.
the spill increasing?
Okay, when we do this, I needed to write this out. When we do this, we have the equation, which goes here, okay? And then we have things that we know, and then what we're trying to find. Every time you do one of these problems, we're going to have an equation, what we know, what we're trying to find, okay? Got it? All right, things that we know. We know that the radius is increasing at a rate of 2, right? The radius is increasing at a rate of 2. What variable do we use, or what thing do we use to represent the radius, the rate of the radius changing? What tells us the rate of the radius? Like, what is equal to 2? What's the rate of the radius? That's just the radius. What's the rate of the radius? Rate of change of
2
radius.
feet per second.
No? Like, what variable do we, like, what's equal to 2? I'll give you a hint.
Oh, dr over dt?
Yeah, drdt, right? The rate at which the radius is changing, that's just saying drdt is 2, right? The rate that the radius is changing means drdt is 2. Okay, it says, how fast is the area of the spill increasing? So what are we trying to find?
Feet per second.
No, hold on. What are we trying to find?
dv over dt.
We're trying to find, not dv dt, dA dt, right? That's what we're trying to find. How fast is the area? Fast means the rate of the area, right? Which is dA dt. When the radius is 60. When r is 60. Got it? So 2 things that we know, 1 thing that we're trying to find. Okay, we're going to do this by finding the derivative first, and then we're just going to plug crap in, right? So if we find the derivative of this, what's the derivative of a? 1 dA dt, right? Because everything is respect to time, okay? All right, this guy, pi r squared, to find his derivative, 2 comes down in front, so it's 2 pi r to the first power times
dr dt.
dr dt, right? Everything's with respect to time, okay? So now, can I find the rate at which the area is changing if I just plug the junk in? Yeah. So the radius is 60, and it's changing at a rate of 2 feet per second, right? So, I don't know, 60 times 2 times another 2 is 240.
Yeah.
240 pi. So 240 pi, or, what is that? What's 240 times pi?
240.
Like 800 something.
Oops.
Oh.
753.
753?
754.
754 what?
Oh, 753.98.
Okay. 754 what? Like, what's the units?
Oh, the unit.
Feet
I
per
was so
second,
confused.
right?
The area is square feet per second. It is spilling out at that rate. Does that make sense? The rate that the area is increasing is 754 square feet per second. That's a lot. That seems like a lot. Does that not seem like a lot?
How big is a house?
But the radius is increasing 2 feet per second. That's a lot. Isn't that fast?
It's constant, so it's like exponential.
Yeah. 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 Now,
That's what's up.
this is the thing to note. Ready? Okay. The thing to note is that the area will not always be increasing 754 square feet per second, because kind of like the volume of a balloon, it's probably going to increase really fast and then it's going to slow, right? Okay. So, seconds before this, it might have been increasing at a rate of 900 square feet per second, right? Versus 10 seconds from now, I might be only increasing at 200 square feet per second, right? Because as that thing, it's going to start to slow down. Like the sludge is going to start to slow down as it gets bigger and bigger and bigger. The area is going to increase at a slower rate as it goes out and out and out. Got it?
Not in this scenario.
You don't think so?
It's because the radius is constant.
What?
Is the constant.
No, because like 10 seconds from now, it will. The radius is increasing at a constant rate of 2 feet per second, but okay, you're right. So that is constant. So, but yeah. So like 10 seconds from now, it'll still be increasing at a rate of 2 feet per second, right? Okay, but that won't always be the case. That won't always be the case is what I'm saying. Like 10 seconds from now, it might be only increasing at 1 feet per second, right? Because eventually that tanker is going to start to slow down because it's not going to have as much in it, right? So,
Makes sense to me.
yeah. Anyway, okay, let's go up to example 1. Example 1 has no story problem context to it, but it's a lot easier, right? Here we go. They give us the thing that we need to identify is the equation, what we know, and what we're trying to find. Okay? They give us an equation. What is it?
Y equals x cubed.
Y equals x cubed. We have no story problem context to that problem. That's just what it's giving us, okay? What are we trying to find? dy dt. Okay, so I'm going to put that here. dy dt, that's what we're trying to find. We know that t equals 1. We know that x equals 2. We know that dx dt equals 4 when at the time of 1, right? Okay, dx dt will not always equal 4. Maybe when the time is 2 seconds, dx dt might be 7. I don't know. But at 1 second, the rate of change of x is 4, right? Okay. Okay, so now what?
Plug it all in.
Not yet. We got to take the derivative first. Right? What's the derivative of y?
1.
1.
D y or d.
dy d
X.
t. Everything's related to time now. dy dt. Okay? What's the derivative of x cubed? What's the derivative of x cubed?
3x squared.
3x squared?
dx dt.
dx dt, right? Now I have to put something behind x's, right? Okay, we are trying to find dy dt. That's this guy. So I'm just going to plug numbers in. X is 2. Why did they give me t equals 1? I don't even have a t in my equation. Sometimes they give you things that you don't need. Dx dt is 4. So the rate that y is changing with respect to time is 48. And we don't even have units. 48 inches per second, or
48 t's per
no, something distance per t,
something per t.
right? 48 distance per time. We don't know what the distance is. We don't know what the time is. Okay, got it? Whoa.
That was cool.
Yeah, I don't like example 1 just because there's no story problem context to it, so you don't really understand or get the full feel of it. I like rates of change. I think they're interesting. Whatever. Okay.
Boring.
All right. Boring. Okay. All right. We're going to stop for the day. Bye, Daniel.
Bye, Dan.